everyone, welcome to another two-dimensional kinematics video. This will be on projectile motion example number 5. Determine how much farther a person can jump on the moon as compared to the Earth if the takeoff speed and angle are the same. The acceleration due to gravity on the moon is 1/6 what it is on Earth. Okay, so already we're given something in the problem. We're told that g on the moon is equal to 1/6 the g on Earth. Okay, we don't have to put numbers there. We're going to be fully working with ratios here. Okay, now determine how much farther a person can jump. The distance you jump is a range. Okay, and we actually derived the formula for range back in video number 40. So if you want to see how that formula is derived, or if you don't remember, go back to video 40 and click that, come back and continue watching where you left off. Okay, but in the meantime, recall, okay, we derived the range in video 40 to be, and the range is given by x. X is equal to v naught squared sine 2 theta naught over g. X is your range, v naught is your takeoff speed, theta naught is the initial takeoff angle, g is the acceleration due to gravity, and those are our unknowns. Well, those are the things we're dealing with in that problem. So that's our general statement. Because we're dealing with the moon and Earth here, I want to create two different equations, one for the moon, one for the Earth. Okay, so let's do that right here. So the range on Earth is going to be equal to v naught squared sine 2 theta naught over g Earth. Now, before you ask me why I didn't put v naught Earth, theta naught Earth, that's because it tells you in the question that the takeoff speed and the angle are the same for both of them. So we don't have to give these subscripts because in both cases it'll be identical. Okay, so the next part is the distance covered on the moon. So it's going to be the same, v naught, square that, sine of the 2 times the takeoff angle over g moon. Okay, so we got those two formulas. Next thing I want to do is actually simplify this a bit. I'm going to take the g Earth, multiply it on both sides, so I just get a statement and I don't have a quotient here. So let's rearrange these two equations to get v naught squared sine 2 theta naught equals x Earth g Earth. Okay, and down here, same thing, v naught squared sine 2 theta naught is equal to x moon g moon. Okay, so something that should become very clear at this point is that the left side of both formulas are identical. Okay, so because these two sides are equal to each other, mathematics tells us that the right sides must also be equal. So what we want to do is set these two equal to each other, and we're going to solve for our unknown. So let's go ahead and do that. Okay, so we're going to say x Earth g Earth is equal to x moon g moon. Now, before you think that we have too many unknowns, remember back to the beginning of the problem, we were told that the acceleration due to gravity on the moon is 1/6 what it is on the Earth. So we created a mathematical expression to represent that. G moon equals 1/6 g Earth. So let's use that expression here. Okay, so that means here, this is in fact 1/6 g Earth. So let's plug that in. So we'll have x Earth g Earth equals x moon times 1/6 g Earth. Because on both sides of the equal sign you simply have a product of different things, you can cancel out the g Earths on the left and the right, leaving you with x Earth is equal to 1/6 x moon. So we're not quite done yet because the question says determine how much farther a person can jump on the moon. So we actually have to isolate for x moon. And when you do that, you need to multiply both sides by 6 to cancel out the 1/6 there. And when you do that, you're going to get x moon is equal to 6x Earth. In other words, with the same takeoff speed and the same takeoff angle, on the moon you can jump 6 times as far. Okay, so that's it for this video, guys. As always, if you enjoyed the video, be sure to subscribe to my channel so that you can catch my next video, and give that like button a click. I will see you guys next time.